Okay, in this part of our topic, what we will be doing, we'll be covering four main things: heat capacity, specific heat capacity, latent heat, and specific latent heat. What do they all mean? What's the purpose of it? Okay, so let's start first of all by the basic understanding of it. When you speak of heat capacity, as the name states, capacity, how much it can take, and so we can say that heat capacity, so let me write that down as a definition. Right, so heat capacity, amount of heat energy to change or get a body or mass increased in temperature by 1 degree Celsius. 1 degree Celsius or 1 Kelvin. Okay, 1 Celsius and 1 Kelvin are equal. Remember that 1 degree Celsius is equals to 1 Kelvin, but 1 Kelvin is not on the scale of 1 degree Celsius. All right, now for heat capacity and specific heat capacity, the difference is that when we speak of specific, we need to be specific of what we are talking about. And so with specific capacity, we're talking of a kilogram. So it's the same, almost the same definition, except it's talking about 1 kilogram of mass increased by 1 degree Celsius. Okay, that is in summary time. This one here, it is just for a mass to increase by 1 degree Celsius. All right, so that's the difference. This is talking about 1 kilogram. So let's see, where do we work with this example? Energy for this one here will be equal, energy is equals to mass times specific capacity times the change in temperature. All right, so consider a say warm water bottle of containing 150 kilograms of, say, cold water or cool water at 10 degrees Celsius. It's not ice, it is cold. All right, so I want you to calculate the amount of energy required to raise the temperature of the water to 80 degrees Celsius. So let's see what you have been given. Okay, so in this problem here, I always look at the equation. We are talking within the same state. It is not changing state, it is only increasing temperature or decreasing temperature. That is the key point. So since we have identified that it's only changing temperature, this is the equation which we'll be using. It did not change state. All right, so what you do is you state what you've been given. I have been given that we're talking of 1 kilogram. Okay, it is originally at 10 degrees Celsius and it raised to 80 degrees Celsius. All right, so we put here the mass is equals to 150 kilograms. The change in temperature is from 10 to 80. But you will not say 10 minus 80. You're going to say the big one minus the small one, which gives us 70 degrees Celsius increase in temperature, or 70 Celsius having been increased. Now, calculate the amount of heat energy. Well, we need the specific heat capacity of water. Why the specific heat capacity of water? Because it is within the state of water. All right, it is not changing state. So we need to know the amount of energy the water can take before it changes state. So the specific heat capacity of water is 4200 joules per kilogram Celsius, or per Kelvin. Okay, now you would usually be given these values, so there's no need to memorize them. All right, so we come now and we look at the equation. Amount of energy will be mass, specific heat capacity, then the change in temperature. The mass is 150 kilograms, which we have there, times the specific heat capacity, joules per kilogram Celsius, times the change in temperature, which is 70 degrees Celsius. So we do our calculations. We get our calculator and we say 150 times 4200 times 70, and that gives us that big value. So we get 44100,000 joules. Notice the kilograms will cancel and the Celsius will cancel. We don't usually write this big number, so I want you to use what you have learned. So this is 44 times 10 to the 6th power joules. If you don't want to use this, you then say 44 times 10, or not times, what do you put, or 44 megajoules. M stands for the 10 to the 6th power. Okay, or we put 4.4 times 10 megajoules, because this will give us back the 4. All right, so we end up with that. So that is how you calculate the amount of energy that it is required for it to change temperature, not change state. Okay, this is the amount of energy it would require to observe, to be that the cold water we need to take for it to become still a liquid, but with a temperature up to 80. Now, the amount of energy it would release from here back to 10 would be the same. What does that mean? That if you have a water or a container of water of 80 kilograms, no, 80 at 80 degrees Celsius, and that water is to be left to cool down to 10 degrees Celsius, and let's say we're talking of 150 kilograms, the same thing, then how much energy will be lost to the atmosphere? It will be the same as this, because nothing has been added or again, it is just being lost to the atmosphere, the heat energy. Okay, so this is with specific heat capacity. So okay, this next problem is in respect to this same question here, but a follow-up. How much energy will it take for this quantity of water to change to steam? Okay, we're not worried about what temperature it is, we're just worried about how much energy will it take to be changed to steam. So let me change the problem here and word it, because our end of the day is to combine the two problems. So how much energy will be needed to convert 150 kilograms of boiling water to steam? It will not go through a temperature change, it will just go through a change in state, and this is known as latent heat. Okay, and because we're talking of vaporization, then this is what you will be using. Amount of energy is equal to a latent heat of vaporization times the mass. Okay, so the latent heat of vaporization you are given for water. So latent heat of vaporization is 230000 joules per kilogram. Notice it doesn't say anything about temperature, just per mass. So you have the mass now to equal to 150 kilograms. So you will substitute these two values into your equation. Usually you're given this. If not, you may be asked to find this. Right? That doesn't mean you will get this same value. So you take 20000 joules per kilogram times 150 kilograms. When you multiply those two, you end up with 150 times 2300123 equals, give us that big long value. Okay, so let me write that down on our paper. 350345. Okay, I'm joules, or 345 megajoules, or 3.45 times 10 to the second power megajoules. It's the same thing. Now note here, this is the amount of energy it requires for 150 kilograms of water to become steam. Okay, so amount of energy required of ice to become water now, or water to become ice. Consider now, and this is very unique, and I want you to pay keen attention to this piece here, as this kind of question always comes up in your CXC. How much energy will be needed or lost to convert 150 kilograms of cold water to ice? All right, so what happens here is that the latent heat of solidification is 34000 joules per kilogram. I want this amount of water to be turned to ice. I'm not interested at what temperature the water is. I just want to know the amount of energy for it to change to ice. How much is being lost, not gained in this case. In this case, it is gaining because it is becoming more volatile. In this case, it is being lost because it is cooling down. All right, so take note, getting hotter, getting cooler or cold. So equation still it applies. Energy is equals to latent heat of solidification times the mass, which is equals 34000 joules per kilogram times 150 kilograms. So take our calculator, we say 150 times 340123 equals, we get 5100000 joules, or 51 megajoules, or 5.1 times 10 megajoules. Okay, so that is what we get. Now look at this. This is less energy than this. Okay, so we get the 150, we get 5.1 megajoules. Here we get 345 megajoules. Here we get 51 megajoules. It takes, so here we can see that here we have more energy at the changing of this state compared to this one here. Okay, and so here is where the concept of bonding comes in with chemistry, and you start to combine them. I want you to take note also that if I was to take cold water and I want to get that water boiling, that amount of energy will be less compared to changing that water to steam. What does that mean? Let's see. Remember here we have 150 kilograms. So let's say that we have 150 kilograms of cold water. I want that to heat up to 100 degrees Celsius. How much energy will it take? Well, heat energy is equals mass, specific heat capacity times the change in temperature. The mass is still 150 kilograms. The specific heat capacity of water bring the old problem that we had. Is it specific capacity of water? Here it is. We'll say consistent 42. We take 4200 joules per kilogram Celsius times 100 degrees Celsius, because that is the change in temperature it will undergo. So punch into our calculator, we get 150 times 4200 times 100, and that gives us 63 million. So you get 63 joules or 63 megajoules. Note that amount of energy. Note this amount of energy. Okay, so it takes more energy for that water to change state. Okay, that same mass of water to change state compared to get that water from cold water to 100 degrees Celsius just to boil. Okay, so it takes this. So I want you to go. Okay, so basically put that as a question, as a forum. So after viewing this video, I hope you can analyze the questions carefully and use them to apply. Okay, so in this topic, in this video, we'll be covering the concept of this first one, where we got a body of water which was at 10 degrees Celsius to heat it to 80 degrees Celsius, change in temperature without any changing in state. And then we got it to change state, how much energy would be required. So now we're going to take that same problem, modify it slightly, and combine the concept. We have a container of water which has 150 kilograms, and that is at say 10 degrees Celsius. It is heated to reach to the state of steam and boils. Okay, so I want to know how much energy does it take to go from this point to become completely steam. All right, so what do we need? We need to find the amount of energy for it to change temperature, which is energy equals mass, specific heat capacity times the change in temperature. For it to change state now, we just need the energy, latent heat of vaporization times the mass. So therefore the total amount of energy will be mass, specific heat capacity times change in temperature plus the latent heat of vaporization times the mass. Notice how the equation can get more complicated. Alright, we could factorize out the m if we want, or we can leave it there. That's up to you. So what is it that we know? We do know from the concept that the specific capacity of water is 4200 joules per kilogram Celsius. We know that the latent heat of vaporization is 340,123 joules per kilogram, right? and we know that the mass is still at 150 kilograms. Now why is it that we include mass here and mass here? Well, because it is this mass that will change temperature, and that same mass will then be converted to a different state. So that amount of mass needs to be multiplied by the amount of heat by the latent heat of vaporization. So we put into our calculations, mass 150 kilograms times specific heat capacity for 200 joules per kilogram per Celsius times the change in temperature. Well, it went from 10 to here, which will be 100 degrees Celsius. We are talking of 90 degrees Celsius plus the latent heat of vaporization, joules per kilogram, times the mass, which is still 150 kilograms because it doesn't change, and so that becomes our equation. Okay, it is still a small equation, don't worry about that piece there. So we take our calculator and we punch in those values into it. So we get 150 times 4200 times 90 equals plus open bracket 340,000 times 150 close bracket equals that amount. So let me write that amount of energy, which is 107,700,000 joules. Okay, so that's the amount of energy it will be required for that 150 kilograms of cold water, which is at 10 degrees, to be converted completely to steam. So notice how we combine the equations. All right, to shorten this up, we can get 107.7 megajoules. Okay, or we can say 1.077 times 10 to the second power megajoules is the same thing. All right, so this is how you combine our equations, and it can get longer. All right, so don't worry how long this gets. Just remember, this is for a change in temperature, this is for a change in state. I need to have a change in temperature before it melts? Yes. Can it have a change in temperature after it has boiled? Yes. All right. So all that is really happening is that the vapor is getting heated up more, and so the molecules start to vibrate even faster, which means it requires much more energy. All right.